Welcome to the mechanics of rest. Somewhere far beyond Neptune, beyond Pluto's long path, and beyond the crowded diagrams that make the solar system look almost tidy, there may be a vast, dim reservoir of ancient ice moving so slowly that even the word distant begins to feel too small. The Oort Cloud has never been photographed as a whole. No spacecraft has reached it. Its bodies do not shine like planets, and most of them may spend millions of years without coming anywhere near the sun. Yet scientists believe it is there because certain comets arrive from directions and distances that seem to require a hidden source. If you enjoy these long, calm journeys through science and space, a gentle like helps more than it may seem. Subscribing also lets Mechanics of Rest keep bringing new explorations each week, made for curious minds at the end of the day. The true scale of the Oort Cloud is not only a matter of distance. It is a way of asking where the solar system really ends and how far the sun's quiet influence may continue after the planets have fallen far behind. Chapter 1: The First Failure of Ordinary Distance. One astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, and it is already too large for ordinary thought to hold comfortably. It is the kind of distance that has to be learned as a unit rather than carried as an image. Light crosses it in a little more than 8 minutes, which means that sunlight arrives at Earth after a brief delay, not instantly, and every bright afternoon is already receiving the sun as it was a few minutes earlier. For the inner solar system, that unit works well enough. Mercury, Venus, Earth, and Mars can be placed inside it, or just beyond it, and the mind can still keep a rough sense of order. Past Mars, the scale begins to widen in a different way. Jupiter circles the Sun at more than 5 astronomical units, Saturn at nearly 10, Uranus at about 19, and Neptune at about 30. The numbers remain small on a page, but each one is built from the Earth-Sun distance repeated again and again until the space between the planets becomes larger than the entire region where the rocky worlds move. A diagram can place them neatly in a row, but the diagram has already surrendered the truth of proportion. It has made room for names, not distances. Neptune is often treated as the last planet, and in one sense it is. Its orbit forms the outermost path of the 8 recognized planets, a blue world moving through the dimmer sunlight 30 times farther from the sun than Earth. At that distance, the sun is still the center of everything, but it no longer has the familiar force of presence that it has in the inner system. Light is thinner. Warmth is not a condition of the place. The planet's year lasts about 165 Earth years, so one full circuit of Neptune around the sun is longer than the span between many human generations. Pluto complicates the old habit of ending the solar system at Neptune. Its orbit is not a simple outer ring, but a stretched path that carries it inward and outward across a wide range, sometimes nearer to the sun than Neptune, and sometimes much farther away. Pluto belongs to a broader population, the Kuiper Belt, a region of icy bodies beyond Neptune that includes dwarf planets, small worlds, and remnants from the early solar system. The Kuiper Belt is not the Oort Cloud, but it is the first warning that the planets are not the whole structure. Beyond the familiar 8, the solar system becomes less like a set of clean orbits and more like a scattered archive. The Kuiper belt extends roughly from the region beyond Neptune out to about 50 astronomical units, with some related populations reaching farther still. Even that distance is modest compared with what comes later. 50 astronomical units is wide enough to make Earth seem close to the Sun, and Neptune seem only partway out, yet it remains close to the central planetary disk. The bodies there still belong to a flattened region, shaped by the same broad plane in which the planets travel. The Oort Cloud, by contrast, is not usually described as a belt at all. It is thought of as a cloud because its bodies may surround the solar system in a vast, roughly spherical reservoir. The word cloud can be misleading if it suggests mist or visible softness. Nothing like a glowing shell surrounds the Sun at those distances. The Oort Cloud, if seen by some impossible wide survey, would be mostly emptiness, with small icy bodies separated by enormous intervals and moving slowly under the Sun's faint gravitational hold. It is a cloud in the mathematical sense of distribution, not in the weather sense of vapor. Before the Oort Cloud can be understood, ordinary distance has to fail completely. The inner edge of its main region may begin thousands of astronomical units from the Sun, depending on the model being used, while its outer reach may extend tens of thousands of astronomical units, perhaps toward 100,000. Between Neptune at 30 astronomical units and even the nearer parts of the Oort Cloud lies a gulf that makes the planetary solar system seem compact. The familiar planets occupy the bright central neighborhood. The Oort Cloud belongs to the outskirts of the Sun's authority. Voyager 1 gives the scale a useful anchor because it is not a drawing or a thought experiment, but a machine that actually left Earth. Launched in 1977, it passed Jupiter and Saturn, used their gravity to change its course, and continued outward after its planetary work was done. In 2012, instruments aboard Voyager 1 measured conditions, showing that it had crossed the heliopause, the boundary where the solar wind gives way to the surrounding interstellar medium. That crossing was a real boundary, and it mattered. Yet it was not the edge of the solar system if the solar system is measured by the Sun's gravity and by the distant reservoir of bodies still orbiting it. This distinction is one of the first quiet corrections the Oort Cloud requires. Interstellar space can begin before the solar system has ended. The heliosphere is the bubble made by the solar wind, a flowing plasma environment shaped by the Sun's activity. The Oort Cloud is a gravitational structure defined by bodies that may still be bound to the Sun across distances so large that the solar wind has long since faded as a local influence. A spacecraft can cross one boundary and still remain inside the larger family. Voyager 1 and Voyager 2 are often called interstellar spacecraft, and the phrase is correct in the plasma sense. They have moved beyond the main region filled by the Sun's outward-flowing particles. But in Oort Cloud scale, they remain near the beginning of a much longer journey. Estimates often suggest that a Voyager-like spacecraft would require centuries merely to reach the inner region associated with the Oort Cloud, and tens of thousands of years to pass beyond its far side. A human-built object can travel for generations, then civilizations, then written histories, and still only be crossing the Sun's distant outskirts. Distance at that scale becomes less like a line and more like duration. A kilometer no longer helps. Even an astronomical unit begins to feel like a small coin used to count a continent. The Oort Cloud changes measurement into weighting, light hours, light days, spacecraft centuries, orbital periods so long that no single recorded human history could watch one complete return. The sun still holds those bodies, but it holds them lightly, across intervals in which motion appears almost still. The planets move in a relatively flat arrangement because they formed from a disk of material around the young sun. Their paths are not perfectly aligned, but the general plane remains one of the solar system's most visible organizing features. The Oort cloud breaks that visual habit. Long-period comets arrive from many directions, with orbits tilted steeply compared with the planetary plane, and this is part of what led scientists to infer a distant surrounding source rather than a simple outer belt. A flat diagram, once again, is not enough. There is a calm difficulty in this kind of science. The Oort cloud cannot be introduced the way Mars or Saturn can be introduced, by pointing to a world with a disk, a color, a set of moons, or a spacecraft image. It has to be approached through scale, through absence, through the motion of comets that return from distances where the sun is no longer a bright object in any ordinary sense. Its reality is not the reality of a photographed surface. It is the reality of an explanation that keeps answering the same orbital question. At thousands of astronomical units, sunlight would be greatly reduced, not gone, but spread thin across an enormous sphere. A small icy body there would not glow in the dark. It would keep its slow path, reflecting almost nothing back toward the inner solar system, separated from its nearest neighbors by distances that could be planetary in their own right. The cold would not be dramatic. It would be a condition, steady and old, suited to objects that have spent most of solar system history away from heat. The first chapter of the Oort cloud, then, is not a story of discovery yet. It is a story of proportion. Earth's orbit becomes a measuring stick. Neptune becomes a marker. Pluto and the Kuiper belt show that the planets are not the ending, and Voyager shows that even a spacecraft crossing into interstellar space has not crossed the full reach of the sun. Each familiar boundary gives way to a larger one. Each larger one makes the old diagram smaller. By the time the scale has been allowed to open, the Oort cloud is no longer merely a distant region beyond Pluto. It becomes the outer architecture implied by the solar system's longest visitors, the comets whose paths seem to come from a reservoir far beyond the planets. To understand why scientists began to believe in such a reservoir, the chronicle has to move from distance to evidence, from the width of the solar system to the strange persistence of comets that should, over time, have vanished. Chapter 2: Jean Oort and the Comets That Should Have Vanished. Long before the Oort cloud had a name, the problem was already moving through the inner solar system in the form of comets. They appeared near the sun, brightened as their ices warmed, lost dust and gas, and then either returned along known paths or disappeared into the long arithmetic of their orbits. Some came back often enough to be recognized across generations. Others seemed to arrive from distances so large that their previous visits, if they had happened at all, belonged to a world before recorded astronomy. The question was not only where they came from, It was why there were still so many of them. A comet near the sun is not a permanent thing in the same sense that a planet is permanent. Each close passage alters it. Sunlight warms its surface, volatile ices escape, dust lifts away, and a body that may have remained cold for immense spans of time begins to spend itself. Planetary gravity can also change its path, sometimes shortening an orbit, sometimes lengthening it, sometimes removing the comet from the solar system altogether. If long-period comets had been passing close to the sun again and again for the whole age of the solar system, many of them should have faded, broken apart, or been lost. Their continued arrival suggested that the visible comets were only the small returning fraction of a much larger hidden population. This was the kind of problem that suited orbital astronomy, because the evidence was not a surface or a photograph. It was a pattern. Astronomers could record the direction from which comets entered the inner solar system, the shapes of their paths, the steepness of their inclinations, and the enormous distances implied by their periods. A single comet could be treated as an event, but many comets together became a statistical landscape. Their orbits pointed backward, not to a bright place that could be seen, but to a remote reservoir that made sense of their distribution. Ernst Öpik had already suggested, in the early 20th century, that comets might come from a vast distant star surrounding the sun. His work did not give the cloud the name by which it would later be known, but it placed an important idea into the scientific record. The comet supply might not be kept near the planets at all. The planetary region was too active, too disruptive, too warm over time. A longer-lived star would need distance. It would need to keep icy bodies away from repeated solar heating until some small gravitational alteration sent a few of them inward. Jan Oort returned to this problem in 1950 with the careful pressure of numbers. He studied the known orbits of long-period comets and noticed that many seemed to have aphelia at enormous distances, far beyond the planetary region. Their paths did not look as though they came mainly from a flat belt aligned with the planets. They suggested a surrounding distribution, a distant cloud of icy bodies weakly held by the sun. Oort was not discovering the cloud by looking at it. He was discovering the need for it. There is a particular patience in that kind of inference. A comet appears, moves for a time through the observable sky, and then the path calculated from its motion extends far beyond the reach of direct sight. The visible arc is small. The implied orbit is enormous. From that short passage near the sun, astronomers can recover a much larger geometry, as though a brief mark on the edge of a page revealed the curve of a circle too large to draw. The Oort cloud entered science through this discipline of extension, where the seen portion of a path required an unseen place to complete it. Oort's argument also depended on the fragility of comets. If the same long-period comets had been returning from the beginning, their surfaces would not remain unchanged. Repeated solar passages would remove volatile material. Encounters with planets would disturb their orbits. Some would be ejected, and others would become too faint to notice. A continuing supply, therefore, implied a reservoir from which relatively fresh comets could be sent inward. The cloud was not merely a place of storage. It was a way for the solar system to keep renewing one of its most ancient visible phenomena. The comets that mattered most for this reasoning were those with very long periods, often moving on orbits so stretched that they seemed almost parabolic when seen from the inner solar system. Their paths carried them close enough to the sun to become active, then outward again toward distances that dwarfed Neptune's orbit. When enough of these orbits were examined together, their directions appeared too widely distributed to belong only to the familiar planetary plane. This mattered. The planets move in a disk because they formed from a disk, but long-period comets seem to arrive from above, below, and across that plane, as if the source surrounded the solar system rather than encircled it as a narrow ring. The word cloud became useful because it did not force a hard surface onto the idea. It suggested distribution rather than wall, population rather than boundary. Still, the word had to be handled carefully. No mist hung at the edge of the sun's reach. No continuous veil marked the place where the planets ended. The proposed cloud was almost all emptiness, populated by icy bodies so widely separated that even their collective abundance would not make the region visibly bright. Its existence was held in the mathematics of comet paths. By 1950, astronomy had already learned to accept such invisible structures when the evidence required them. Neptune itself had been found through the gravitational disturbance of Uranus before it was seen as a planet. Binary stars, dark companions, unseen masses, and distant objects had often entered scientific thought, first as explanations for motion. Oort's comet cloud belonged to that tradition, but it was more diffuse than a planet and harder to picture than a companion star. It had no single orbit to follow. It was a reservoir, a population spread across a volume of space so large that even the word outer became inadequate. The hidden population also had to be old. The solar system formed about 4.6 billion years ago, and any explanation of long-period comets had to survive that depth of time. A nearby store would be too easily disturbed or depleted. A distant one could preserve icy bodies in cold storage, away from the repeated heating that alters comet surfaces. At such distances, a body could remain almost unchanged for immense intervals, carrying material from the early solar system until a passing star, the galactic tide, or some other small influence adjusted its path. Then, after a silence longer than civilizations, it might begin to fall sunward. This cold storage was not stillness in the absolute sense. Every object in the proposed cloud would be moving, orbiting, responding to gravity. Yet the motion would be so slow and the orbits so large that change would occur at a pace unlike anything in the inner solar system. A comet near Earth can cross the sky from night to night. An Oort Cloud body in its distant orbit may spend most of its existence in a region where sunlight is only a faint condition, and the sun is less a blazing presence than the central mass to which the orbit remains tied. The body keeps its path because gravity continues to reach it, even when light and warmth have become thin. Oort's proposal gave long-period comets a home, but it also changed the solar system's shape. The solar system was no longer only a flat arrangement of planets, asteroids, and nearer icy bodies. It also included a much larger surrounding structure, one inferred from the way comets entered the planetary region after long absences. That structure did not replace the planetary disk. It enclosed it at a distance, or at least surrounded it in the loose statistical sense that models could support. The sun, in this picture, governed not only the familiar worlds, but also a remote population whose members were rarely seen. The idea was powerful because it answered more than one difficulty at once. It explained why long-period comets could still appear after billions of years. It explained why their inclinations were widely distributed. It explained why some seemed dynamically new, arriving as though their surfaces had not been repeatedly exhausted by close solar passages. A good scientific explanation often has this quality. It does not merely patch a single hole, it makes several separate observations belong to the same architecture. There remained, however, a useful uncertainty. The Oort cloud was not directly observed in Oort's time, and it has not been directly imaged as a complete structure since. Its population, its total mass, its inner and outer limits, and its detailed shape remain subjects of modeling and revision. The evidence supports a distant comet reservoir, but the reservoir is not a photographed shell with a measured surface. It is an inferred region, made scientifically durable by the repeated behavior of objects that become visible only after they have already left it. That distinction gives the Oort cloud much of its character. It is one of the solar system's largest proposed structures, yet it is known through small temporary visitors. A comet brightening near the sun is a local event, but its orbit may carry the memory of a region thousands or tens of thousands of astronomical units away. The inner solar system receives the messenger, and the mathematics points back to the source. In this way, the Oort cloud is not silent because it has no evidence. It speaks through arrivals. Once Oort's idea is in place, the first chapter's problem of distance becomes tied to a second problem, the problem of renewal. The planets and the Kuiper belt show that the solar system extends far beyond Earth. The comets show that something still farther out may feed the inner solar system with ancient ice. To understand that connection more closely, the chronicle has to follow one of those bodies inward, not as a symbol of mystery, but as a physical object with a nucleus, an orbit, a history of cold, and a brief season of light. Chapter 3: What a Long-Period Comet Remembers. A comet entering the inner solar system is a small body carrying a very long history into a brief interval of warmth. For most of its existence, it may have remained far from the sun, moving through a region where ordinary sunlight had little power to change its surface. Then its orbit bends inward, not because the body has chosen a new character, but because gravity has revised the path it was already following. By the time it becomes visible from Earth, the most important part of its journey has usually happened unseen. The visible comet is only the warmed portion of a much larger story. At its center is the nucleus, a body of ice, dust, rock, and frozen volatile compounds, often only a few kilometers or tens of kilometers across. Near the sun, some of its ices change directly into gas, lifting dust from the surface and forming the coma, the diffuse envelope that can make the comet appear much larger than the nucleus itself. Solar radiation and the solar wind shape the escaping material into tails, so the comet becomes a bright object not because it is large like a planet, but because a small ancient body is being altered by heat. That alteration is part of what makes comets scientifically valuable. A comet is not a pure, untouched sample in any simple sense, because every close solar passage changes it. Yet it may still preserve material from the solar system's early formation, especially if it has spent most of its life in deep cold and only recently entered the inner planetary region. Its surface may have been processed, darkened, fractured, or depleted, while deeper layers may still carry older chemistry. The object is therefore both archive and weathered page, a remnant whose history has to be read with care. Edmund Halley's work gives a useful doorway into this subject because he showed that at least some comets were not one-time apparitions. In the early 18th century, Halley compared recorded comet appearances from 1531, 1607, and 1682, and argued that they were returns of the same body moving on a long elliptical orbit. The comet later known by his name returned in 1758 after Halley's death, confirming that comets could be members of the solar system rather than atmospheric omens or wandering strangers. Its period of roughly 76 years was long by human standards, but still short enough for historical records to recognize the pattern. Halley's comet belongs to a different rhythm from the most distant long-period comets. Its orbit carries it beyond Neptune, but not into the full remoteness associated with the outer Oort Cloud. It returns often enough that human generations can expect it, miss it, record it, and prepare for it again. Long-period comets from the Oort Cloud may have periods of thousands, tens of thousands, or even millions of years. For them, return is not a family memory. It is an event separated from its previous passage by spans that erase ordinary continuity. This difference matters because a comet's period is not only a number, it is a measure of exposure. A short period comet has approached the sun many times, and each approach has drawn material away from it. Its surface may become less active, its volatile materials may be depleted, and its orbit may be reshaped by repeated planetary encounters. A long-period comet arriving from the Oort Cloud may be making one of its first passages through the inner solar system, or at least its first after an interval so long that the surface has remained in deep storage. The light that reveals it also begins to change it. The orbit provides the deeper clue. Perihelion is the point where the comet comes closest to the sun, and aphelion is the farthest point in its path. In a long-period comet, the path may be so stretched that its farthest distance lies thousands or tens of thousands of astronomical units away. The body sweeps through the inner solar system relatively quickly, then spends almost all of its existence in the outer reaches of its orbit. What seems, from Earth, like the comet's appearance is only a small bright segment of an enormous ellipse. Inclination adds another part of the memory. Many long-period comets do not stay close to the plane in which the planets orbit. They can arrive from steep angles, moving through the inner solar system from directions that do not fit a flat disk alone. This is one of the reasons the Oort Cloud is imagined as a surrounding reservoir rather than only an outer belt. The comet's path carries a trace of the structure it came from. Its angle is a quiet line drawn back toward a distant distribution. The body itself does not know the word reservoir, but its motion keeps the record. In the far reaches of its orbit, the comet remains cold enough for many volatile materials to persist. Frozen carbon monoxide, carbon dioxide, methane, ammonia, water ice, and dust may be present in different proportions, depending on where and how the body formed and how much it has been altered. When the comet approaches the sun, the more volatile substances can begin escaping at large distances, while water ice becomes more active nearer the inner solar system. The changing activity becomes a physical report from the nucleus. A comet's memory, then, is chemical as well as orbital. It remembers formation in the substances it carries. It remembers storage in the cold preservation of those substances. It remembers disturbance in the shape of the orbit that sent it inward. Once it comes near the sun, it begins to remember heat through loss, jets, dust trails, and surface changes. Nothing in that memory is written as a sentence, but each part can be measured, compared, and placed inside the long history of the solar system. Spacecraft encounters have helped make that history less abstract. Missions such as Giotto at Halley's Comet, Stardust at Wild 2, Deep Impact at Tempel 1, and Rosetta at 67P Churyumov-Gerasimenko showed that comet nuclei are not smooth, icy spheres. They are dark, irregular, layered, fractured, and active in uneven ways. Rosetta's long study of 67P revealed cliffs, pits, dust-covered terrains, and jets emerging from particular regions as the comet warmed. These are not Oort Cloud objects in the simplest category, but they show what a cometary nucleus can be, a small world whose surface records repeated episodes of heating and loss. The Oort Cloud body, before its return, would have known a different condition. Far from the sun, there is no thick atmosphere to stir, no weather in the planetary sense, no day of warmth followed by a night of cooling as Earth understands it. There is only a slow orbit, a surface held at low temperature and sunlight weakened by distance until it becomes less an environment than a faint input. Dust and ice remain together. Volatile compounds that would not last long near the sun can persist. The body is not waiting in any conscious sense, but its material condition is one of preservation. When such a body begins to come inward, the change is gradual long before it becomes visible to the naked eye or even to many telescopes. More volatile ices may begin to escape while the comet is still beyond the orbit of Jupiter or Saturn. Dust may loosen. The nucleus may develop a faint coma that grows as it approaches stronger sunlight. By the time observers on Earth see a bright comet, the inner solar system is receiving the late luminous part of a process that began much farther out. This is why long-period comets are more than celestial visitors. They are moving samples from a reservoir that cannot be sampled directly. Their orbits suggest the architecture of the Oort Cloud, while their chemistry suggests something about the materials stored there. Each one is incomplete evidence because its path has been perturbed and its surface altered, but incomplete evidence can still be valuable when many examples are gathered. The cloud itself remains unseen. The comets become its brief readable edges. Some long-period comets do not return. A gravitational encounter with Jupiter or another planet may place a comet on a path that carries it away from the sun permanently. Others may break apart, fade, or become too depleted to produce a visible coma. A few may be captured into shorter period orbits becoming more frequent visitors to the planetary region. The Oort Cloud is therefore not only a storage place, but part of a larger exchange where bodies can be sent inward, transformed, lost, or reassigned to new orbital families. The distinction between different comet families is useful, but it should not become too rigid in the mind. Halley-type comets, Jupiter family comets, and long-period comets describe patterns of motion and likely source regions, not separate kinds of substance sealed away from one another. The Kuiper belt and scattered disk are strongly associated with many shorter period comets, while the Oort cloud is associated with long-period ones. Still, orbital histories can be complicated. The solar system sorts its small bodies through gravity over long intervals, and the categories are ways of reading the sorting rather than walls within it. A long-period comet arriving from the Oort cloud has traveled through a geometry that is difficult to compress into ordinary narration. Most of its orbit lies outside the region where planets move, outside the region where sunlight dominates physical change, and outside the region that telescopes can easily survey for such small bodies. Then, for a short span, it enters the part of the solar system where human instruments are waiting. The old ice warms, the dust lifts, the orbit is measured, and a body that spent almost all of its life in obscurity becomes evidence. In that evidence, Jean Oort's distant reservoir becomes less like a theoretical convenience and more like a necessary background to the comets themselves. The comet's nucleus carries early material. Its path carries the shape of a vast orbit. Its inclination carries the hint of a surrounding source. Its activity near the sun carries the cost of becoming visible. To understand how so many icy bodies reached such distant storage in the first place, the chronicle has to turn back from the returning comet to the young solar system, where the giant planets were not only worlds in formation, but forces capable of sending small bodies outward into the sun's farthest keeping. Chapter 4. The young solar system sends its small bodies outward. The Oort cloud did not begin where it now appears to reside. Its icy bodies are thought to have formed much closer to the young sun, inside the broad region where the giant planets were taking shape, and where the early solar system still contained more leftover material than the present arrangement suggests. In that earlier time, the planets were not finished worlds moving through a cleared architecture. They were growing masses inside a disk of gas, dust, ice, rock, and smaller planetesimals, all sharing the same central gravity, but not yet settled into the sparse order now seen around the sun. About 4.6 billion years ago, the solar system formed from a collapsing cloud of gas and dust. Most of the mass gathered into the sun, while the remaining material flattened into a rotating protoplanetary disk around it. Near the sun, heat made it difficult for volatile ices to persist, so rocky materials dominated the inner region. Farther out, where temperatures were lower, water ice and other frozen compounds could become part of the solid material from which larger bodies grew. That colder outer disk became the nursery for many of the small icy bodies that later entered cometary history. Planetesimals were the intermediate pieces in this slow construction. They were not dust grains, and they were not planets. They were small bodies, ranging from modest fragments to objects many kilometers across, large enough to have gravity and collisions matter, but still vulnerable to being moved by larger neighbors. Some joined growing planets. Some remained as smaller populations. Others came under the influence of the giant planets and began the long process of being scattered into different parts of the solar system. Jupiter mattered first because of its mass. It became the largest planet, more massive than all the other planets combined, and its gravity shaped the motion of nearby bodies with unusual authority. Saturn, Uranus, and Neptune also participated in the sorting, especially in the colder outer regions where icy planetesimals were more common. A small body passing near one of these planets could have its orbit altered, gaining or losing orbital energy depending on the geometry of the encounter. The encounter did not need to be a collision. Gravity alone was enough. This is one of the quieter powers of a planet. It can rearrange bodies without touching them. A planetesimal approaches, curves through the planet's gravitational influence, and leaves on a different path from the one it carried before. Repeated many times, across millions of years, and across countless small bodies, this process becomes a form of architecture. The giant planets did not merely occupy the young solar system. They helped decide which small bodies remained near them, which were thrown inward, which were sent outward, and which were lost from the sun altogether. Some of the bodies sent outward would not have escaped completely. Their orbits stretched, becoming much larger than the region in which they formed. A planet might lift the far end of a small body's orbit to great distance, while the sun still retained enough gravitational hold to keep it from becoming interstellar. Later, the weak influence of passing stars and the galactic tide could raise the nearer part of the orbit, separating the body from repeated encounters with the planets. In this way, a planetesimal first scattered outward by a giant planet could become stored far beyond the planetary region. The path from the early outer disk to the Oort Cloud was therefore not a single movement. It was a sequence of changes, each one modest when considered alone, but large in consequence when combined over time. A body formed in the cold regions near the growing giant planets. A close gravitational passage altered its orbit. A second encounter changed it further. At great distance, external influences helped detach the orbit from the planetary zone. After enough such changes, the body no longer belonged to the busy inner architecture of the solar system, but to the remote population surrounding it. The nice model gives one formal way of thinking about this early rearrangement. Developed to explain several features of the solar system's present structure, it proposes that the giant planets did not always occupy their current orbits. Their migration, driven partly by interactions with a massive disk of smaller bodies, could have disturbed large populations of planetesimals and sent them into new regions. In this framework, the outer solar system was not born already calm. Its present order emerged after a long period of exchange between planets and small bodies. The model is not a preserved film of the early solar system. It is a reconstruction built from present-day orbits, computer simulations, crater records, and the distribution of small body populations. Its details have been revised, debated, and refined, as models of deep history often are. Still, it captures a central idea that remains important for the Oort Cloud. The giant planets were not passive markers in a finished system. Their movement and gravity help scatter icy material outward, making a distant comet reservoir possible. In the young solar system, density mattered. There were far more small bodies available for scattering than there are now in the planetary region. The space between the growing planets was not empty in the modern sense. It contained material that could be absorbed, broken apart, moved inward, sent outward, or ejected entirely. Every planetesimal had its own path, but the collective result was a slow thinning of the disk. The young solar system was clearing itself, and the Oort Cloud may be one of the places where some of that cleared material survived. The difference between ejection and storage was delicate. A body given too much energy by Jupiter or another planet could leave the sun's gravity altogether, becoming an interstellar object before such objects were ever detected passing through our system. A body given less energy might remain bound, but on an orbit so extended that it spent almost all its time far from the planets. At those distances, additional small influences could change the orbit again, lifting it away from the planetary region and making it less likely to be disturbed on every return. The Oort Cloud formed, in this view, from bodies that were sent far away but not quite lost. There is no need to imagine this as a sudden outward flight. The process is better understood as gradual redistribution. A young planetesimal's orbit lengthens. Its farthest point moves outward. Its next passage near a giant planet changes the path again, or perhaps prevents another close passage from occurring. The sun remains central, but the body's life becomes less tied to the bright, crowded region where planets move. Across enough time, the object enters a colder and more distant rhythm, one in which a single orbit can become longer than the entire history of human civilization. This history explains why Oort Cloud bodies are usually described as ancient. They are not new objects formed at the edge of the sun's reach. They are likely old material stored at the edge after being displaced from the formative regions of the solar system. Their ices, dust, and frozen compounds belong to the chemistry of the early disk. Their present distance belongs to the later consequences of gravitational scattering. A comet returning from the Oort Cloud therefore carries two histories at once: the place where its material formed and the long path by which that material was sent outward. The giant planets also shaped different reservoirs in different ways. The Kuiper Belt preserved part of the outer solar system's small body population closer to the planetary plane, while the scattered disk contains objects whose orbits were more strongly altered by Neptune. The Oort Cloud reaches into a different scale, where the original planetary scattering was later softened and widened by external influences. These regions are related by history, not identical in structure. Together they show that the solar system's small bodies were sorted into many forms of survival. Neptune's role is especially important near the outer planetary region. Its gravity has shaped the Kuiper Belt, trapped some bodies in orbital resonances, and scattered others into more eccentric paths. But Neptune alone does not account for the full Oort Cloud. The vast surrounding reservoir requires a longer chain of events involving the giant planets as a group and the later action of weak external forces. The Oort Cloud is therefore not merely beyond Neptune in distance. It is beyond Neptune in the kind of history required to produce it. A young solar system that sends small bodies outward also keeps part of its own beginning at a distance. Near the planets, surfaces are warmed, struck, altered, differentiated, and rearranged. Farther out, change slows. In the cold storage of remote orbits, some materials can persist with fewer episodes of heating. This does not make Oort cloud bodies perfectly untouched, but it does make them valuable. They may preserve chemical clues from the era when planets were still assembling and the Sun was still surrounded by the remains of its birth disk. By the end of this early sorting, the solar system had become more than a set of planets. It had a central star, a planetary disk, belts and scattered populations of smaller bodies, and a remote reservoir built from the consequences of formation. The Oort cloud, in this view, is not an afterthought placed at the boundary. It is part of the solar system's own making, created when the largest planets gave small, icy bodies new paths, and the wider galaxy helped lift some of those paths into distant storage. The next question is what kind of structure that storage became. A belt can be pictured as a flattened region, a disk-like population connected to the plane of the planets. The Oort cloud requires a wider geometry, with an inner region, an outer region, and a surrounding distribution so large that its shape is easier to describe through models than through images. To follow the bodies outward is therefore to arrive at the shell that is not a wall, the broad reservoir where distance becomes volume. Chapter 5: The Shell That Is Not a Wall. At the distance where the Oort cloud begins to matter, the solar system no longer behaves like the familiar drawing of rings around a star. The planets occupy a flattened arrangement, and the Kuiper belt still belongs broadly to that same plane, even though its objects are not as orderly as the planets themselves. But the Oort cloud is usually described in a different geometry. It is not a belt laid around the sun like a wide road. It is a surrounding reservoir, a distant population that may extend above, below, and around the planetary disk until the solar system becomes less like a plate and more like a volume. The word shell is useful, but only if it is kept gentle. A shell can sound like a surface, a hard outer boundary, something with an inside and an outside clearly divided from each other. The Oort cloud is not thought to be that kind of structure. No spacecraft would pass through a shining membrane. No visible wall would appear at a certain distance from the sun. What changes is not the presence of a surface, but the probability of finding icy bodies on enormous, weakly held orbits, spread so sparsely that the space between them remains almost the whole story. Estimates for the Oort cloud's inner and outer boundaries vary because the structure is inferred rather than directly mapped. Some descriptions place the inner region at roughly a few thousand astronomical units from the Sun, while other scale descriptions refer to the main cloud beginning nearer 1,000 astronomical units. The outer reach is often placed somewhere around 100,000 astronomical units, though this too is a model-dependent boundary rather than a measured edge. These numbers are not fence posts. They are ways of speaking about a population that becomes more or less likely across distance. 1,000 astronomical units already belongs to a different order of distance from the planets. Neptune, at about 30 astronomical units, lies far from Earth in ordinary terms, yet it is still close to the Sun compared with the near side of the Oort cloud. Move from Neptune to 1,000 astronomical units, and the Sun's planetary family shrinks toward the center. Continue outward to tens of thousands of astronomical units, and the planets become a small inner arrangement inside a far larger gravitational domain. The distances do not merely increase, they change the meaning of what counts as near. The inner Oort cloud is often associated with the Hills cloud, named for the astronomer Jack G. Hills, who argued that a denser inner reservoir could help replenish the more distant outer cloud. This idea matters because the outermost bodies are more exposed to perturbations from passing stars and the broader gravitational field of the Milky Way. A more compact inner store, still far beyond the planets but less weakly held than the outer cloud, could preserve material over long periods and supply bodies outward or inward as orbits changed. In this view, the Oort cloud is not one simple layer. It has an inner depth and an outer reach. Hills's contribution gave the distant reservoir a more durable architecture. If only the outer cloud existed, the population might be depleted too easily over the age of the solar system. Passing stars and galactic tides could send some bodies inward as comets, but they could also remove bodies from the sun's control altogether. A denser inner component would act as a longer-lived store, less exposed than the outermost cloud, yet still remote enough to avoid the repeated planetary encounters that alter comets near the sun. The Oort cloud became, through this reasoning, not only a cloud of possible comets, but a layered system of preservation and loss. The outer Oort cloud is the region most often imagined when the name is used loosely. It is the vast spherical reservoir from which many long-period comets are thought to come. Its bodies may orbit so far from the sun that the difference between solar gravity and outside influence becomes delicate. The sun still binds them, but faintly. A small disturbance, accumulated over long intervals, can alter the orbit enough to send an object inward or ease it away toward interstellar space. The outer cloud is therefore both part of the solar system and exposed to the environment beyond it. The spherical shape is not a decorative idea. It arises from the behavior of long-period comets, whose orbits arrive from many inclinations rather than from a single flat plane. If their source were mainly a disk like the Kuiper belt, more of their paths would be expected to preserve that flattened geometry. Instead, the distribution suggests that many have been randomized over time, their orbits lifted and tilted by the slow action of stellar passages and the galactic tide. The cloud's shape is therefore a record of long exposure to weak forces. There is a difference between being scattered outward and being rounded into a cloud. The early giant planets may have sent icy bodies onto stretched orbits, but those initial paths would still have carried traces of the planetary disk. Over time, external gravitational influences could change the orientations of those orbits. A population that began with disk-like origins could become more nearly spherical in distribution, not because it formed as a sphere, but because the galaxy and passing stars gradually loosened its memory of the original plane. The Oort cloud's shape, in that sense, is a later chapter in the history of scattered planetesimals. A body in the inner Oort cloud would not experience the same gravitational environment as one near the outer edge. Closer in, the sun's hold is stronger, and outside influences work more slowly. Farther out, solar gravity becomes weaker, and the boundary between retention and loss becomes easier to cross. The same object shifted slightly in energy might remain bound for immense spans or leave the solar system completely. The cloud is therefore not a static warehouse. It is a distribution of different degrees of belonging. Distance becomes volume here, and volume changes intuition. A line from the Sun to Neptune can be imagined as an extension of the planetary system. A line from the Sun to the Oort Cloud is harder, but still possible as a sequence of markers. A sphere with a radius of tens of thousands of astronomical units is different. The space it encloses grows with the cube of its distance, so the outer reservoir occupies a volume so large that the bright planetary region becomes a small central detail. The Oort Cloud is not merely farther away than the planets. It surrounds their scale and makes it seem local. Inside such a volume, even a huge number of icy bodies would be spread thinly. Estimates of the Oort Cloud's population can reach into the billions or trillions of comet-like objects, depending on size assumptions and models. But abundance does not mean crowding. The bodies could be separated by enormous distances, with each one moving through its own long orbit in a darkness that is mostly empty space. The cloud may be immense in total population and still almost vacant at any single place. That is one of the quiet contradictions of astronomical scale. A structure can be real, populous, and sparse at the same time. The outer boundary is especially difficult to define because it depends on what it means for an object to belong to the Sun. At small distances, belonging is obvious. Earth orbits the Sun, Neptune orbits the Sun, and their paths are not in practical doubt. At the edge of the Oort Cloud, the Sun's gravity competes more evenly with the gravitational field of the galaxy and with the passing influence of other stars. An object may remain bound for a time, then be nudged away. Another may be barely retained. The boundary is not a line, but a long fading of control. This fading control is why the Oort Cloud is sometimes treated as the outermost extent of the solar system. The heliopause, where the solar wind gives way to interstellar plasma, is much closer. The Oort Cloud lies far beyond that plasma boundary, in the region where the Sun's gravitational influence still has meaning. If the solar system is defined by particles carried by the solar wind, its edge is one thing. If it is defined by bodies orbiting the Sun, its edge is much farther away. The Oort Cloud forces those definitions to stand apart. The phrase true scale becomes important here. A schoolroom solar system often ends with Neptune, perhaps with Pluto set just beyond, and sometimes with a faint belt of icy objects after that. Such a picture is not wrong for the planets, but it becomes deeply incomplete for the Sun's full reach. The Oort Cloud stretches the solar system into a structure whose outer regions are not visited by spacecraft, not illuminated enough to be seen directly, and not arranged in a simple plane. It is the part of the solar system most easily erased by diagrams because it is too large to fit them honestly. Yet the cloud does not need to be pictured as a lonely emptiness detached from everything else. It is connected to the inner solar system by comets, to the early solar system by formation history, and to the galaxy by the perturbations that reshape its orbits. Its bodies may have formed near the giant planets, been scattered outward, preserved in cold storage and later disturbed into new paths. The architecture is distant, but the chain of causes is continuous. The same sun that warms Earth holds, faintly, the farthest icy bodies in that reservoir. A useful way to think of the Oort cloud is as a gradient of memory and influence. Nearer the sun, the memory of the planetary disk remains stronger. Farther out, the influence of the galaxy becomes more important. In the inner cloud, bodies may be stored with less frequent disturbance. In the outer cloud, some are nudged inward and become long-period comets, while others are gradually lost. The structure is therefore not a perfect sphere of ice, but a broad region where the solar system's past and its stellar environment meet. By the end of this geometry, the shell has become something other than a wall. It is an extended population, layered, sparse, unstable at its margins, and held together by weak gravity across a scale that makes the planets seem close to home. The next step is to understand why such a distant structure is so easily disturbed. Once the sun's grip becomes gentle enough, the Oort cloud no longer belongs only to the sun's history. It also begins to respond to the slow tide of the Milky Way and to the passing of other stars through the wider neighborhood. Chapter 6: Where the sun's grip becomes gentle. At the outer reaches of the Oort cloud, the sun still matters, but it matters in a different way. Near Earth, solar gravity is the central fact of motion, strong enough that the planet's yearly path can be treated as a stable, repeating arrangement. Near Neptune, the sun remains plainly dominant even across 30 astronomical units of distance. Farther out, across thousands and tens of thousands of astronomical units, that dominance softens. The sun is still the mass around which an Oort cloud body moves, but the wider galaxy begins to have a visible place in the calculation. Gravity weakens with distance, and this simple fact quietly changes the character of the solar system. An icy body in the inner Oort cloud may remain more firmly attached to the sun than one in the outer cloud, where the same star's pull is spread across an immense separation. Nothing abrupt happens at a single line. There is no moment when solar authority disappears. Instead, belonging becomes gradual, a condition measured by orbital energy, external influence, and the long patience of time. The word grip can be useful, though it should not be imagined as a hand closing around an object. The sun holds the planets through gravity, and it holds the Oort cloud through gravity as well, but not with equal strength. At large distances, a small outside influence can alter an orbit in ways that would be negligible closer in. A passing star, the collective tide of the Milky Way, or a massive cloud of interstellar gas can slightly revise the path of a distant cometary body. Over enough time, a slight revision may become the beginning of a much larger change. This is why the Oort cloud is not only the sun's outer storehouse. It is also the part of the solar system most exposed to its surroundings. The planets move inside a comparatively protected region where the sun's gravity overwhelms most external disturbances. The outer Oort cloud lies where that protection has thinned. It is still solar, still part of the sun's extended family, but it is also open to the slow presence of the Milky Way. The boundary between system and environment becomes less like a border and more like an area of negotiation. The galactic tide is one of the main influences in that outer region. The Milky Way is not only a bright band across the sky as seen from Earth, it is a vast gravitational structure made of stars, gas, dust, dark matter, and the mass distributed through its disk and halo. The Sun orbits within that structure, and the Oort Cloud travels with it. Across the immense width of the cloud, the galaxy's gravitational field is not perfectly uniform. The tiny difference from one side of the cloud to another can slowly change the orbits of distant icy bodies. This difference is called a tide because it resembles, in a broad physical sense, the way one gravitational field can stretch or alter motions across an extended region. It is not a tide of water. Nothing rises and falls as an ocean does. Instead, distant orbits are gently reshaped by a field that is almost steady over human time, but persistent over astronomical time. A body that would otherwise continue in a long, cold orbit may have its path altered enough that its closest approach to the sun begins to change. That change can protect it from planets, send it inward toward them, or help loosen it from the sun altogether. The scale of the effect is small in any ordinary moment. A single year means almost nothing to an object whose orbit may take millions of years. Even 1,000 years can be only a short passage in a larger cycle. But the Oort Cloud is a region where weak influences are given enormous time in which to work. A small gravitational bias, repeated across long intervals, can become the reason a body that spent most of solar system history in distant storage eventually enters the inner system as a long-period comet. Passing stars add another source of disturbance. The sun is not fixed in an empty background. It moves through the galaxy, and other stars move as well, each carrying its own gravitational field. Most pass at distances too large to matter greatly, but over billions of years, some come close enough to influence the outer Oort cloud. They do not need to enter the planetary region. They do not need to come near Neptune or even the Kuiper belt. At Oort cloud distances, a star passing within a light year or so may have a measurable effect on the orbits of the most distant bodies. Skol's star gives a named example of this kind of encounter. It is a small binary system, a red dwarf with a brown dwarf companion, whose motion indicates that it passed through the sun's extended outer neighborhood roughly 70,000 years ago. The passage was not close in planetary terms. It did not disturb Earth, change Neptune, or rearrange the familiar solar system. But in Oort cloud terms, the event belongs to the relevant scale because the cloud is so large that a star can pass through its outer regions while remaining unimaginably far from the planets. The useful lesson of Scholz's star is not that it caused a visible shower of comets, because such claims require caution. Its value is quieter. It shows that the sun's outer reservoir is not sealed away from stellar traffic. Over the age of the solar system, many stars have passed nearer or farther from the Oort cloud, each adding a small gravitational alteration to some portion of the distant population. Most of these encounters would leave only subtle traces. A few may have helped send comets inward or carry distant bodies away. At such distances, the difference between remaining bound and becoming unbound can be delicate. An object near the outer edge of the Oort cloud may move so slowly relative to the Sun that a modest change in its orbit matters greatly. A passing star can add or remove orbital energy. The galactic tide can lift or lower the closest part of an orbit. A body that once returned toward the Sun after millions of years may be shifted onto a path that never returns. Another, once stored safely far away, may begin the slow inward journey that eventually makes it visible. This does not mean the Oort cloud is chaotic in the dramatic sense. It means that its order is loose. The inner solar system has tight orbits and short periods, with the planets returning again and again on schedules that can be predicted with great precision. The outer cloud has long orbits, weak binding, and accumulated disturbance. Its structure is not disorder, but it is an order that has to include outside influences. The solar system, at its farthest reach, is not an isolated machine. There may also be influences from molecular clouds, the large regions of gas and dust that lie within galaxies and sometimes become the birthplaces of stars. Encounters with such clouds are much rarer in their strong form, and their effects depend on mass, distance, and the Sun's path through the galaxy. Still, over long spans, the wider galactic environment cannot be ignored. The Oort cloud is wide enough and loosely held enough that the surrounding medium becomes part of its history, even if only occasionally and unevenly. The idea of the Sun's Hill sphere helps give this exposure a rough conceptual frame. A Hill sphere is the region around a body where its gravity dominates the motion of smaller objects against the background influence of a larger system. For the Sun, the larger system is the galaxy itself. The Oort cloud lies within the Sun's broad gravitational domain, but near the outer parts of that domain the distinction becomes less secure. The Sun can keep many bodies, but it cannot keep all of them forever. This makes the Oort cloud a region of slow exchange. Some bodies remain in long storage. Some are nudged inward and become comets. Some are lifted into safer orbits away from planetary encounters. Some are lost to interstellar space. Over billions of years, the population changes, not through a single event, but through the steady arithmetic of weak gravity and large numbers. The cloud survives because it is large and numerous. It changes because its margins are exposed. There is a quiet significance in the fact that the same forces that threaten the cloud also help reveal it. Without perturbations, many distant bodies might remain remote indefinitely, never entering the inner solar system where they can become visible. The galactic tide and passing stars disturb the reservoir, but disturbance is also what sends some of its members toward the Sun. The Oort cloud is therefore known partly because it is not perfectly stable. Its slight vulnerability becomes the path by which evidence arrives. The Sun's grip, then, is neither absent nor absolute. It is strong enough to preserve a distant population over the age of the solar system, yet gentle enough that the galaxy can participate in the motion of its outer bodies. This balance gives the Oort cloud its special place in solar system science. It is not merely far away. It is far enough for the Sun and the Milky Way to share influence over the same small icy objects. Once that balance is understood, the return of a long-period comet becomes easier to place. A body does not leave the Oort cloud because the cloud has a gate, or because the inner solar system calls it inward. It leaves because a distant orbit has been altered, sometimes only slightly at first, until its path carries it back towards stronger sunlight and the planetary region. The next chapter follows that return, where a small change at the edge of the sun's reach can become, after a long interval, the visible passage of a comet through the inner solar system. Chapter 7: The Long Fall Back Toward Light. A long-period comet does not begin its return with brightness. It begins as a distant body whose orbit has been changed just enough for the old path to become a new one. Far out in the Oort Cloud, where the sun's gravity is still present but softened by distance, a small icy object may move for millions of years without entering the planetary region. Then a passing star, the galactic tide, or some combination of weak influences alters the orbit by a small amount. The change may be slight in the place where it happens, but across an orbit measured in thousands of astronomical units, slight changes can become a new destiny. The important alteration often concerns perihelion, the point where the body comes closest to the sun. An object may already be bound to the sun, already moving along a vast path, but if its perihelion remains far beyond the planets, it will never become a visible comet from Earth. It will stay in cold storage, part of the remote population, scientifically important but unseen. If a perturbation lowers that perihelion enough, the same object may begin to pass through the region where sunlight can warm its surface and where telescopes can notice its arrival. In that lowering of the closest point, the cloud begins to speak. This is not a quick fall in the ordinary sense. The comet may spend an immense span moving inward, closing the distance gradually across a path so large that most of the journey remains outside human observation. Near the outer cloud, its motion is slow, and the sun is only the central mass that keeps the orbit bound. Farther inward, the sun's pull strengthens, and the body's speed increases along the long curve of its path. The orbit gathers it toward the center, not as a straight descent, but as a stretched return through the geometry of gravity. For most of that return, nothing visible happens. The nucleus remains small and dark. It reflects little light. Its surface stays cold enough for many ices to remain locked inside or just beneath a dusty crust. Against the background of the sky, it would be too faint, too remote, and too slow for ordinary detection. The comet exists as a moving body long before it becomes a visible event. Its arrival begins in mathematics before it begins in light. As it comes closer, the first physical changes depend on what it carries. More volatile ices, such as carbon monoxide or carbon dioxide, can begin to escape at larger distances from the sun than water ice can. This early activity may form a faint coma while the comet is still beyond the orbit of Jupiter, sometimes even farther out. Dust loosens and drifts away from the surface. Gas carries fine material into the surrounding space. The nucleus, still only a small object, begins to surround itself with the sign by which comets become known. A comet's brightness is therefore not a direct measure of its size alone. A small active nucleus can produce a large coma, while a larger but less active one may remain less conspicuous. The visible head of the comet is a temporary atmosphere of escaping material, not a solid surface. Tails form as sunlight and the solar wind act on that material, separating dust and ionized gas into structures that point according to forces acting near the sun. The comet appears to grow because it is losing itself. That loss is part of every return. Each approach to the sun removes material that cannot easily be replaced. Jets may open from certain regions, dust may settle back in other places, and the surface may darken as volatile materials are depleted. A dynamically new comet, one making perhaps its first close passage from the Oort Cloud into the inner solar system, may behave differently from a comet that has already passed near the sun many times. Its surface may still carry more easily released material. Its activity may begin earlier or change less predictably as heat reaches layers that have not recently been exposed. The phrase dynamically new has to be handled carefully. It does not mean newly made. It means new to the inner solar system in an orbital sense, or at least new enough that its previous close approaches have not strongly shaped its present condition. Such a comet may be nearly as old as the solar system itself, formed among the icy planetesimals of the early disk and stored far away for billions of years. Its novelty is not age, but encounter. The sun is receiving an ancient object under comparatively fresh circumstances. Planetary gravity then becomes important again. A comet entering the region of Jupiter, Saturn, Uranus, and Neptune does not move through an empty corridor. The giant planets are small compared with the distances between them, but their gravitational influence can still change an orbit sharply by celestial standards. Jupiter especially can shorten a comet's period, lengthen it, redirect it, or help remove it from the solar system. A body sent inward from the Oort Cloud may therefore not simply return to the same distant storage after one passage. Its future can be revised by the planets it encounters. Some comets become periodic visitors after such changes. Others are placed on paths that take them away forever, no longer bound to the sun. A few pass close enough to the sun to fragment or fade, their material spread into dust streams or lost into space. Many remain too faint to become famous, leaving only orbital records and survey detections. The visible history of comets is therefore a filtered history. The bright ones remembered by observers are only the most noticeable members of a much larger traffic of small bodies moving through the sun's domain. Comet C 2013 A1 Siding Spring offers a clear example of a long-period comet entering the planetary neighborhood. Discovered in 2013 from Siding Spring Observatory in Australia, it passed close to Mars in October 2014, close enough that spacecraft orbiting Mars were used to study both the comet and its effects on the Martian environment. Its orbit indicated a source in the distant Oort Cloud, making its passage a rare chance to observe a body that had spent most of its existence far from the sun. The comet did not need to become a grand object in Earth's sky to matter scientifically. Its path was enough to connect Mars, spacecraft, and the far comet reservoir in one measured event. That encounter with Mars also showed how an Oort Cloud comet can enter the inner solar system as a visitor from another scale. Mars is a world mapped by orbiters and rovers, a planet with seasons, dust, polar ice, and a known place in the inner solar system's geography. Siding Spring came from a region so distant that its previous orbital history reached beyond ordinary planetary time. For a short interval, those two histories crossed, a nearby planet with human machines around it, and a small icy body from the sun's outer store. The crossing was temporary, but the scientific connection was durable. The comet's passage did not require drama to be meaningful. Dust from the comet interacted with Mars's upper atmosphere, and instruments studied the composition of gases and particles released by the comet. Such measurements matter because they turn an arrival into evidence. A long-period comet can be examined through its coma, its dust, its gas, its orbit, and its response to sunlight. Every measured feature becomes one more limited but useful report from a region that cannot yet be visited. A comet sent inward from the Oort Cloud also carries uncertainty. Its original orbit may have been altered before discovery, and the measured path may need careful correction for gravitational and non-gravitational effects. Jets from the nucleus can slightly change motion by releasing gas in uneven directions. Planetary encounters can revise the orbit further. The comet's present track is therefore both evidence and outcome, a record of the distant reservoir, and a path continually edited by the forces it meets along the way. The return toward the sun is also a return toward change. In the outer cloud, a body may remain cold and comparatively preserved. Near the sun, preservation gives way to activity. Frozen compounds escape, dust is lifted, and the nucleus loses material that had remained stored for long intervals. The closer the comet comes, the more the sun changes it. Visibility is purchased through alteration, the same process that allows astronomers to study the comet also ensures that the comet will not remain exactly as it was. This gives long-period comets their particular scientific tenderness. They are not permanent messengers carrying untouched truth. They are fragile, changing objects whose evidence must be gathered while the evidence itself is being transformed. A spectrum of the coma reveals gases that have escaped from the nucleus. Images of the dust show material already leaving. Orbital calculations point back toward a source the comet has departed. Science reads them in motion because stillness is not available. Across the whole Oort cloud, only a small fraction of bodies become visible comets in any given span of human observation. Most remain distant. Many will never enter the inner solar system. Some may be lost before anyone could see them. But because the reservoir may contain vast numbers of icy bodies, even a small rate of inward injection can supply long-period comets over the age of the solar system. The cloud size makes rarity continuous. Individual returns are uncommon. The population is large enough for the inner solar system to keep receiving them. This is the bridge between the remote cloud and the familiar sky. The Oort cloud does not show itself as a photographed structure, but it sends evidence inward one body at a time. A comet's orbit gives the direction of the bridge. Its chemistry gives part of the material history. Its activity shows what happens when ancient ice is returned to sunlight. The inner solar system, with its planets and instruments and observers, becomes the place where the far reservoir briefly becomes readable. By following the comet inward, the unseen cloud becomes less abstract. It is no longer only a shell of possible orbits or a conclusion drawn from statistics. It is the source of bodies that can pass near Mars, brighten near the Sun, lose dust into space, and have their paths measured against the background of stars. Yet the cloud itself remains beyond direct view, and the next difficulty is exactly that. If the Oort cloud is large enough to shape cometary history and important enough to define the solar system's scale, the question becomes why no telescope has simply photographed it, and why science must still know it mainly through the objects that leave it. Chapter 8: Why the Cloud Has No Photograph. No telescope has photographed the Oort cloud as a whole, and this absence is not a weakness in the idea. It is part of the nature of the region. The cloud is too distant, too dark, too sparse, and too cold to present itself as an ordinary astronomical object. It does not shine by its own light. It does not form a bright ring around the sun. It does not gather into a surface that can be aimed at, exposed, and resolved. If the Oort cloud is there, it is there mostly as scattered small bodies moving through an enormous volume of space, each one reflecting only a faint trace of sunlight across distances that make even reflected light a poor messenger. The planets are easy by comparison, though even they were not always easy in human history. Mars can be seen by the naked eye. Jupiter and Saturn were known before the telescope. Uranus was first recognized as a planet after telescopic observation, and Neptune was found after mathematics pointed astronomers toward the place where a new planet should be. Pluto, smaller and fainter, required photographic plates and patient comparison. With each step outward, the solar system demanded more from instruments. The Oort cloud asks for something beyond that sequence, because its objects are not one large world at a known distance, but many small bodies dispersed across a region so large that searching it directly becomes a different kind of problem. A body in the Oort cloud would be faint for several reasons at once. It would be small, perhaps only a few kilometers across in many cases. It would be dark because cometary surfaces often reflect little sunlight. It would be far from the sun, so the light reaching it would already be weak. Then the small amount of light reflected from its surface would have to travel back across that same enormous distance toward Earth or toward a telescope near Earth. The result is not merely dimness. It is dimness multiplied by distance, spread over a sky full of other faint points and moving so slowly that recognition becomes difficult. Astronomers often detect distant solar system bodies by their motion against background stars. A nearby asteroid shifts its position more quickly from night to night. A Kuiper Belt object moves more slowly, but still enough for careful surveys to identify it across repeated images. An Oort cloud body in distant storage would move with a far subtler apparent shift. Its motion might be too slight across the timescale of a survey, and its reflected light too weak to stand out clearly. It would be present, but present in the way a nearly erased mark is present on a page. Not absent, yet not easily separable from the background. This is why the cloud is known through inference rather than portraiture. A photograph gives a certain kind of comfort because it seems to place an object plainly before the eye. But astronomy has never depended only on pictures. It has measured motion, brightness, spectrum, timing, gravitational influence, and the repeated behavior of bodies too small or too distant to resolve. The Oort Cloud belongs to this older and more patient tradition. Its evidence arrives not as an image of the reservoir, but as comets whose orbits point back toward one. The difficulty is also geometric. A telescope sees a narrow region of sky at a time, or surveys wider regions to limited depth. The Oort Cloud, if it surrounds the solar system in a broad distribution, occupies no single compact patch. It would extend around the Sun, and from Earth the possible directions of its bodies would cover the sky. Searching for one inactive Oort Cloud object would mean finding a very faint, very slow-moving point among countless other faint points. Searching for the whole cloud would mean turning a sparse population into a map across a volume that cannot be entered and measured directly. Comets become easier to observe only after they have left that distant storage. As a body approaches the Sun, warming begins to alter it. Escaping gas and lifted dust create a coma, and the comet grows brighter than its bare nucleus would be. The same object that was almost impossible to see in the Oort Cloud may become detectable once sunlight has begun to change it. Visibility, again, comes with transformation. The cloud itself remains dark, while its departing members become readable only after they are no longer resting in their distant state. Infrared astronomy can help with cold and dusty objects, but it does not solve every distance problem. An object must still produce or reflect enough radiation to be detected above the sensitivity limits of the instrument. A small, icy body at Oort Cloud distances would be extremely cold and faint. Its heat signal would be weak and its apparent motion slow. Infrared surveys have been valuable for studying comets, asteroids, and other small bodies nearer the Sun, but the remote cloud remains beyond the reach of direct population mapping. The absence of a full image is therefore expected, not surprising. NEOWISE provides a useful example of what instruments can do when an object comes within reach. Originally launched as WISE, the Wide Field Infrared Survey Explorer, the mission surveyed the sky in infrared wavelengths, detecting heat from asteroids, comets, and other objects that might be difficult to study in visible light alone. In its extended NEOWISE mission, it continued observing near-Earth objects and cometary bodies. The instrument did not photograph the Oort Cloud as a structure. Instead, it studied objects whose properties and orbits could help scientists understand the populations from which such objects come. Comet C2006 W3 Christensen became one of the bodies observed in infrared by the mission. Its activity, dust and gas, could be studied because the comet had entered a region where its material was responding to solar heating and where instruments could detect the results. Such observations show the method at the heart of comet science. The reservoir remains distant, but the returning object becomes measurable. Its light, heat, spectrum, dust production, and orbit serve as indirect reports from a place too remote for direct survey. There is a quiet asymmetry in this arrangement. The Oort Cloud may be one of the largest structures associated with the Sun, yet the evidence for it often fits inside the observation of a single comet. A few points of motion across the sky, a calculated orbit, a measured coma, a spectrum of escaping gas, and a comparison with other long-period comets together become part of the argument for a vast reservoir. The smallness of the evidence does not make it trivial. It shows how astronomy often turns limited access into large-scale knowledge. The same principle appears throughout the history of science. Atoms were inferred long before they were imaged in any modern sense. The interiors of stars are known through light, mass, pressure, and theory, rather than direct entry. The center of Earth is understood through seismic waves, not by excavation. In each case, a hidden structure becomes scientifically real because its effects are consistent, measurable, and difficult to explain without it. The Oort Cloud belongs to that company of inferred places, not because it is vague, but because its direct appearance is beyond present reach. Still, inference has different strengths depending on the evidence behind it. The Oort Cloud is not known with the same precision as the orbit of Mars or the mass of Jupiter. Its total population is uncertain. Its mass is uncertain. Its inner boundary, outer boundary, and exact shape depend on models that may be revised as more comets and distant objects are discovered. The basic idea of a remote comet reservoir is strong, but the details remain open. A calm account of the Oort Cloud has to hold both facts together. The reservoir is well motivated, and its full map is not yet drawn. Survey astronomy continues to improve the situation. Wide-field telescopes scan large areas of sky repeatedly, finding moving objects that earlier observers would have missed. Digital detectors replaced photographic plates, automated pipelines compare images, and computing power allows enormous catalogs to be searched for motion. These advances have transformed knowledge of near-Earth asteroids, Kuiper belt objects, centaurs, and comets. They have also made the outer solar system less empty in the scientific imagination. Each new distant object sharpens the question of how small body populations are arranged beyond Neptune. Yet even powerful surveys face the same basic limits. A body that is too faint cannot be found merely by wishing the exposure deeper. A body that moves too slowly may not reveal itself clearly over the time available. A population spread across the whole sky may require repeated observations across many years. The Oort Cloud's difficulty is therefore not one obstacle, but a stack of obstacles. Distance, size, darkness, sparse distribution, slow motion, and the confusion of background sources. Each one narrows the path toward detection. The Vera C. Rubin Observatory, with its wide-field survey of the southern sky, is expected to expand knowledge of the outer solar system by discovering many faint-moving objects. It may find distant comets and unusual trans-Neptunian objects that help refine models of the Oort Cloud and its inner extensions. But even such an instrument will not turn the entire cloud into a visible sphere. It will add pieces, improve statistics, and perhaps reveal objects that sit closer to the boundary between known distant populations and the inferred inner cloud. The map will grow by detections, not by one grand photograph. There is a useful humility in that method. Science does not always advance by making the invisible suddenly visible. Sometimes it advances by making the invisible more constrained. A region that once had only a rough outline gains better limits. A population once estimated broadly becomes narrower in number. An orbit that once seemed unusual becomes part of a pattern, or remains unusual enough to demand a new explanation. The Oort Cloud is being approached in this way, through constraints, returns, and the slow accumulation of better evidence. The absence of a photograph also protects the subject from false simplicity. A photograph might tempt the mind to treat the Oort cloud as a thing with a neat edge and a clean shape. The evidence instead suggests gradients, layers, losses, perturbations, and uncertain boundaries. The cloud is not one object waiting to be framed. It is a population shaped by formation, scattering, galactic tide, stellar passage, and time. Its invisibility is not only an observational limitation, it is a reminder that some structures are better understood as histories than as scenes. For a listener used to images of planets, nebulae, and galaxies, this can feel like a strange kind of knowledge. The Oort cloud is among the most distant parts of the solar system, and yet it has no familiar face. It is known through objects that leave it, through the mathematics of their returns, and through the absence of any nearer reservoir sufficient to explain them. Such knowledge is less immediate than a photograph, but it can be just as disciplined. The mind learns not to ask only what has been seen, but what the seen motions require. By the end of the observational problem, the Oort cloud remains unpictured, but not unsupported. Its existence is held in comet orbits, in the depletion problem that Jan Oort addressed, in the wide inclinations of long-period comets, and in models of how the young solar system scattered icy planetesimals outward. The unseen cloud becomes a structure assembled from returning bodies and weak forces. The next boundary to separate is not between seen and unseen, but between two different meanings of leaving the sun, crossing the heliopause into interstellar plasma, and still remaining far inside the sun's greater gravitational reach. Chapter 9: Two Edges of the Same Solar System. The heliopause is a real boundary, but it is not the same boundary as the Oort cloud. It belongs to the sun's wind, not to the sun's full gravitational reach. For much of the solar system, the sun sends out a flow of charged particles, the solar wind, and that flow fills a large surrounding region called the heliosphere. Eventually, the outward pressure of that solar wind weakens enough to meet the pressure of the interstellar medium, the thin material between the stars. The place where that change occurs is called the heliopause. This boundary has been crossed by human spacecraft. Voyager 1 crossed it in 2012 after decades of travel outward from the planetary region, and Voyager 2 crossed it later, giving scientists a second passage through the outer edge of the heliosphere. Their instruments measured changes in charged particles, magnetic fields, and the surrounding plasma environment. These measurements showed that the spacecraft had entered interstellar space in the sense that they were no longer moving inside the main bubble shaped by the solar wind. It was a careful physical discovery, made not by sight but by particles and fields. Yet the phrase interstellar space can easily mislead. It sounds final, as though the spacecraft had passed the last possession of the sun. In one sense, they had left the sun's plasma environment. In another, much larger sense, they had not left the solar system at all. They were still vastly closer to the planets than to the Oort cloud's far side. They were still moving through a region where the sun's gravity remains the central fact of their long outbound paths. This is the first distinction the Oort cloud asks the mind to keep. The sun influences space in more than one way. It shines. It sends out particles. It holds bodies through gravity. These influences do not end at the same distance. Light continues outward indefinitely, growing weaker with distance. The solar wind has a boundary where it meets the surrounding interstellar medium. Gravity has no hard wall, but its practical dominance fades gradually as other gravitational influences become more important. The heliopause is one edge. The Oort cloud belongs to another kind of edge altogether. The heliosphere can be thought of as the sun's surrounding plasma region. Inside it, the solar wind expands outward, carrying magnetic fields and charged particles from the sun into space. The shape of the heliosphere is influenced by the sun's motion through the local interstellar medium, by the solar cycle, and by the pressure of material beyond it. It is not a perfect sphere, and it is not fixed like a solid surface. It breathes and shifts over time, changing with solar activity and with the conditions outside it. The Oort cloud, by contrast, is not made of solar wind. It is a distant population of icy bodies whose orbits may still be bound to the sun. It is defined less by particles flowing outward and more by small worlds moving around a central mass across enormous distances. A body in the Oort cloud does not need to sit inside the heliosphere to belong to the solar system gravitationally. It can be far beyond the plasma bubble and still remain part of the sun's extended family. This is why a spacecraft can enter interstellar plasma long before it approaches the Oort cloud. Voyager 1's crossing in 2012 gives this distinction a concrete form. After launch in 1977, the spacecraft moved past Jupiter and Saturn, then continued outward along an escape path. When it reached the heliopause, it had traveled farther than any earlier spacecraft, and its instruments recorded a new environment. But if the Oort cloud's inner region lies hundreds or thousands of astronomical units away, Voyager had only begun the larger journey. By Oort cloud standards, even the most distant spacecraft remains near the inner margin of the sun's full scale. There is a quiet humility in that measurement. A machine can leave Earth, pass the giant planets, cross the heliopause, enter interstellar space, and still remain far from the solar system's outer gravitational reservoir. The achievement is not reduced by this. It is clarified. Voyager's journey shows that the solar system has layers, and that leaving one layer is not the same as leaving them all. The heliopause is a boundary of environment. The Oort cloud is a boundary of belonging. Voyager 2's crossing deepened the picture because it took a different path and carried a working plasma instrument. Its measurements help scientists compare conditions at another location along the heliopause, showing that the boundary is not a simple uniform shell. The two spacecraft did not cross at the same place or under the same solar conditions. Their data made the heliosphere more physical, more measurable, and less like a diagram. Even here, at the closer edge, the sun's boundary is shaped, variable, and complex. The interstellar medium beyond the heliopause is thin, but it is not nothing. It contains gas, dust, magnetic fields, cosmic rays, and the larger environment through which the sun travels as it orbits the center of the Milky Way. Compared with air on Earth, it is almost empty. Compared with a perfect vacuum, it is material enough to matter. The heliosphere forms because the sun's outward flow meets this medium, and the balance between them creates a boundary that can be crossed, measured, and studied. The Oort cloud lies in a different relationship with that same galactic environment. Its outer bodies are not protected by the solar wind in the ordinary sense, but they are still connected to the sun by gravity. Passing stars and the galactic tide can alter their orbits, as the previous chapter described, yet those perturbations act on bodies that may remain solar system members for billions of years. A comet in the Oort cloud may move through interstellar plasma while still orbiting the sun. This is the layered nature of the outer solar system. Interstellar medium can occupy space that is still gravitationally solar. Such layering can seem strange only because diagrams tend to give each object one border. Earth has a surface. Jupiter has cloud tops. Saturn has rings. Neptune has an orbit that can be drawn as a line, but the sun's influence does not have one clean outline. The solar wind ends at one kind of boundary. Planetary orbits end much closer in. The Kuiper belt extends beyond Neptune, but remains far inside the Oort cloud. The distant comet reservoir extends beyond the heliosphere and fades into the gravitational environment of the galaxy. Each layer answers a different question. If the question is where the planets end, Neptune provides one answer. If the question is where the solar wind stops dominating the local plasma environment, the heliopause provides another. If the question is where small bodies can still orbit the sun on long, weakly held paths, the Oort cloud stretches the answer much farther outward. None of these answers cancels the others. They belong to different meanings of edge. The difficulty comes only when one boundary is asked to do the work of all of them. The language of interstellar space is especially delicate. Voyager 1 and Voyager 2 are called interstellar spacecraft because they have entered the medium between stars. That phrase is correct and earned. Their instruments are sampling a region beyond the heliopause, and that region is not dominated by the solar wind in the same way as the space closer to the sun. But interstellar does not mean free from the sun's gravity. It does not mean beyond every object that may still orbit the sun. In the Oort cloud scale, interstellar space begins inside a larger solar structure. This layered view also helps explain why the Oort cloud cannot be reached simply by crossing the heliopause. The heliopause lies at a distance measured in hundreds of astronomical units, depending on direction and solar conditions. The Oort cloud's inner regions are much farther away, and its outer regions farther still. A spacecraft traveling at Voyager-like speeds would need centuries to reach even the inner cloud and tens of thousands of years to pass beyond its broad outer domain. The numbers turn one boundary crossing into an early milestone rather than an ending. At those distances, the sun becomes less a source of felt light and more a source of orbital authority. Near Earth, sunlight shapes weather, climate, biology, and the rhythm of days. Near the heliopause, the solar wind still carries a signature of the sun, though weakened and pressed by the surrounding medium. In the Oort cloud, sunlight is faint, but gravity still gives many bodies their paths. The solar system is therefore not only a region of brightness, it is also a region of motion organized around a star. A comet returning from the Oort cloud crosses these layers in reverse. It may begin far beyond the heliosphere, in a place where the surrounding plasma belongs to the interstellar medium. Its orbit, however, still belongs to the Sun. As it moves inward, it passes into the region where solar wind fills space more strongly, then eventually enters the planetary system where sunlight warms its ices and planets can alter its path. The comet's journey shows that these boundaries are permeable. They are crossed not only by spacecraft moving outward, but by ancient small bodies moving inward. The heliopause, then, is not made less important by the Oort cloud. It is important in its own domain. It marks the place where the sun's atmosphere-like extension gives way to the material between stars. It allows scientists to study how a star carves out a bubble as it moves through the galaxy. It gives Voyager's instruments a boundary to measure, and it gives heliophysics a frontier of particles, fields, and pressure. The mistake would be to treat it as the final edge of the solar system in every sense. The Oort cloud adds a slower and larger definition. It says that the Sun's family includes bodies far beyond the solar wind's main reach, bodies so distant that the galaxy can tug at their orbits and passing stars can help decide their futures. It turns the solar system from a bright inner environment into a gravitational structure embedded inside interstellar space. The result is not one boundary but several, nested and overlapping, each belonging to a different physical influence. This is why the true scale of the Oort cloud is also a lesson in definitions. The edge of a system depends on what part of the system is being measured. Plasma has one edge. Planets have another. Small, icy bodies on immense orbits have another still. When all three are placed together, the solar system becomes less like a circle around the sun and more like a set of fading influences, some ending sooner, some continuing for a very long way. The next question rises from that incompleteness. If the Oort cloud is so far beyond the heliopause, and if many of its bodies remain unseen, then the few known objects beyond Neptune become especially important. Some of them do not fit comfortably into the familiar Kuiper belt. Their orbits are detached, stretched, and difficult to explain with the planets alone. Among them, Sedna stands out, not because it is the Oort cloud itself, but because it hints at an outer solar system whose map is still unfinished. Chapter 10: Sedna and the Incomplete Map. Sedna did not fit neatly into the old map. When it was discovered in 2003, it was not simply another small icy world beyond Neptune, nor did it behave like an ordinary member of the Kuiper belt. Its orbit was too stretched, too detached, too remote at its nearest approach to the sun. It seemed to belong to a region where the known planets no longer had an easy explanation for everything, and where the outer solar system began to look less like a finished diagram than a field of missing causes. The discovery came from a survey using the Samuel Oschin telescope at Palomar Observatory, where Mike Brown, Chad Trujillo, and David Rabinowitz were searching for distant objects near the edge of the known solar system. Sedna was first seen as a faint point that shifted against the background stars, and that small motion carried the first clue to its distance. It was not bright, not large in the planetary sense, and not close enough for surface detail to be resolved. It entered knowledge as many distant bodies do, as a measured displacement across images, a point whose position changed just enough to become a world. Follow-up observations were needed before the orbit could take shape. A distant object seen only briefly may be difficult to place, because a small arc of motion can belong to several possible paths. As more measurements were gathered, Sedna's orbit became stranger rather than simpler. Its closest approach to the Sun, its perihelion, lay around 76 astronomical units, far beyond Neptune's orbit at about 30 astronomical units. Its farthest distance carried it hundreds of astronomical units outward. Its orbital period was not measured in decades or centuries alone, but in many thousands of years. That high perihelion was the important part. Many scattered disk objects have stretched orbits because Neptune has altered their paths, but they still come close enough to Neptune for its gravity to remain part of their story. Sedna did not. At its closest, it remained too far away for ordinary repeated encounters with Neptune to explain its orbit comfortably. It was detached, not in the sense of being free from the Sun, but in the sense of being separated from the familiar machinery that shapes much of the region beyond Neptune. The map had acquired an object that seemed to remember a force no longer obvious nearby. At first, Sedna was sometimes described as a possible inner Oort Cloud object. That phrase carried a careful uncertainty. Sedna was far too close to be part of the classical outer Oort Cloud, the remote spherical reservoir associated with many long-period comets. Yet it was too detached to fit easily among the more familiar trans-Neptunian populations. It occupied a transitional imagination, a place between the known Kuiper belt and the vast inferred comet cloud. Its orbit suggested that the outer solar system might contain a population of bodies whose histories were only partly connected to Neptune. The name Sedna, drawn from Inuit tradition, was chosen in part because the object seemed to inhabit an extremely cold and remote region. In scientific terms, however, the more important feature was not the name, but the orbit. A distant body can be interesting because of its size, its surface color, or its brightness, but Sedna's deepest importance was dynamical. It asked how a small world could have been placed on such a path. Its orbit became a question preserved in motion. Several explanations were possible, and none could be treated too lightly. Sedna might have been influenced by a passing star when the Sun was young and still near its birth cluster. It might have been affected by a more massive planet that once existed or still exists in the outer solar system. It might preserve evidence of early solar system conditions that are no longer present. Each possibility points to a different kind of history, and each shows why detached objects matter. They are not merely distant. They are records of an outer architecture that may have changed. The young sun probably formed in a stellar nursery with other stars nearby, not in the relative isolation it occupies now. In such an environment, stellar passages could have been more frequent and closer than they are today. A neighboring star passing near the young solar system might have lifted the perihelia of some distant objects, detaching them from Neptune's influence and placing them on long, stable orbits. If Sedna formed closer to the planetary region and was later altered in this way, its present orbit could be a fossil of the Sun's earliest neighborhood. That idea gives Sedna a different kind of significance from a planet or a comet. It may not only record the solar system's internal scattering, it may record the environment in which the Sun was born. A small body moving silently through the outer dark could preserve, in the shape of its orbit, the gravitational memory of stars that have long since moved away. The present solar system would then contain traces not only of its own planets, but of the cluster from which it emerged. This is one of the subtler gifts of distant orbits. They can keep evidence after the original setting has vanished. Other detached objects made the question wider. 2012 VP113, discovered by Chad Trujillo and Scott Shepard, had a perihelion even farther from the Sun than Sedna's, around 80 astronomical units. It too belonged to the small class of distant bodies that do not come close enough to Neptune for ordinary scattering to explain their current orbits in a simple way. Its discovery suggested that Sedna might not be alone. A single unusual orbit can be treated as an exception. A second begins to look like the edge of a population. More distant candidates and sednoid objects have continued to complicate the picture. The sample remains small, and the biases in discovery are serious, because telescopes are more likely to find such bodies when they are near perihelion, and therefore closer and brighter than they are during most of their long orbits. Many similar objects, if they exist, may spend most of their time far beyond detectability. The known group may therefore be only the near, visible portion of a much larger detached population. The absence of many detections does not yet mean absence of many bodies. The difficulty is that every known object in this region carries two kinds of uncertainty. First, its own orbit must be measured and refined over time. Second, the discovered sample must be corrected for the ways human surveys search the sky. Telescopes do not look everywhere equally. They do not reach all faintness limits equally. Weather, sky coverage, galactic background, survey cadence, and instrument sensitivity all shape what is found. A pattern in the known objects may reflect the solar system, but it may also reflect the search. This matters especially for the Planet 9 hypothesis. In 2016, Konstantin Batygin and Mike Brown proposed that the clustered orbits of certain distant trans-Neptunian objects might be explained by an undiscovered planet, perhaps several times Earth's mass, moving on a very distant orbit. The proposal gave one possible source for the alignment and detachment of some objects beyond Neptune. It also gave the outer solar system a new and difficult observational target. Yet Planet 9 has not been discovered, and NASA continues to describe it as hypothetical, with debate remaining over whether it exists. The hypothesis must therefore be spoken of in a steady register. It is not a confirmed planet hiding just beyond a curtain. It is a proposed explanation for certain orbital patterns, one that has motivated searches and arguments. Some evidence has been interpreted as supportive. Other analyses have emphasized observational bias, small number statistics, or newly discovered objects that do not fit the simplest clustering picture. The scientific value of the idea does not require certainty. It lies in the way it has forced more careful attention to the outer solar system's incomplete map. Detached objects can also be explained without a present, undiscovered planet. Stellar encounters, early cluster effects, planetary migration, rogue planets passing through the young solar system, or a planet that once existed and was later removed, could all, in different models, help produce high perihelion distant orbits. Some of these explanations may work better for certain objects than others. Some may overlap rather than exclude one another. The outer solar system's present architecture may have more than one cause, layered across the Sun's formation environment, planetary history, and long-term gravitational evolution. This is why Sedna remains important even without resolving the larger debate. It is an anchor point for uncertainty, a measured body whose orbit refuses to let the old map close too early. Its existence does not prove the Oort Cloud directly, nor does it prove Planet 9. It shows that the region beyond Neptune contains dynamical structures still being uncovered. The familiar categories, Kuiper belt, scattered disk, inner Oort cloud, detached object, are useful, but the bodies themselves may occupy transitions that language has to follow rather than command. The inner Oort cloud, if it exists as a substantial population, would be especially difficult to distinguish from other distant populations. Objects there would be too far for regular detection unless they came near enough in their orbits to be seen. Their paths might overlap conceptually with detached trans-Neptunian objects, sednoids, and the extended scattered disk. A boundary drawn in a paper may help organize the problem, but the physical solar system does not need to honor the neatness of the boundary. It stores histories in orbits, and those histories can cross categories. Sedna's surface, faint reddish color, and slow path may draw attention, but the deeper story remains gravitational. Something placed it where it is. Something raised or preserved its perihelion. Something allowed it to remain detached from Neptune over long periods. Whether that something was the Sun's birth cluster, an unseen planet, the early migration of giant planets, or a combination of influences, Sedna marks the fact that the outer solar system contains information not yet fully translated. Its orbit is a sentence with missing clauses. The Vera C. Rubin Observatory and other wide-field surveys may change this field substantially. By repeatedly scanning large areas of sky to faint limits, they may discover more distant bodies with unusual orbits, including objects that help distinguish between competing explanations. A larger sample could show whether apparent clustering is real or partly produced by survey bias. It could reveal a broader detached population, find inner Oort cloud candidates, or fail to find the patterns that some models expect. In each case, the map would improve. The important point is that uncertainty here is not emptiness. It is a working uncertainty, full of measurements, models, proposed mechanisms, and difficult observations. The outer solar system is not a blank region into which any idea can be placed. It is constrained by every object discovered, every orbit calculated, every survey that finds nothing where a model expected something, and every new point of motion that appears against background stars. Sedna and 2012 VP113 are small in physical size compared with planets, but they enlarge the scientific problem around them. In the scale of the Oort cloud, Sedna is still relatively near. It does not travel to the outer cloud imagined by Jan Oort, and it does not supply the long-period comets in the simple classical picture. But it belongs to the same broad lesson. The solar system's outer structure is not exhausted by the planets, or even by the Kuiper belt. There are distant populations shaped by weak gravity, old encounters, and incomplete records. The Oort Cloud is the largest of these inferred reservoirs, but it is not the only sign that the edge of the solar system is complicated. By following Sedna, the chronicle reaches a place where known objects and inferred structures begin to overlap. The Oort Cloud remains mostly unseen, while detached bodies offer partial landmarks in the darkness nearer in. Some may be transitional. Some may belong to different histories altogether. The map is not empty and it is not complete. It is a growing arrangement of faint detections, long orbits, and careful restraint. From there, the question naturally widens beyond the Sun. If one planetary system can scatter icy bodies into distant reservoirs, and if one star can preserve a remote archive of its formation, then other stars may carry similar structures beyond the reach of direct sight. Their comets would be harder to study, their reservoirs even harder to map, but the evidence of debris disks and exocomets suggests that the Sun's outer architecture may not be unique. The next chapter moves from Sedna's incomplete map to other suns, where distant reservoirs may also surround planetary systems too faint and too wide to be seen directly. Chapter 11: Other Suns, Other Reservoirs. Not every distant reservoir has to belong to the Sun. The Oort Cloud is the local version of a larger possibility, one that follows naturally from the way planetary systems form. A star gathers material around itself. Planets grow inside the remaining disk. Small bodies are scattered by larger ones, and some of those small bodies may be sent far outward without being lost entirely. Around the Sun, that story leads to the inferred Oort Cloud. Around other stars, the same process may leave reservoirs too distant and too faint to see directly, but not too distant to leave traces. The difficulty is that another star's Oort Cloud would be even harder to observe than the Sun's own. The solar Oort Cloud already has no direct photograph, despite surrounding the star closest to Earth. Around another star, the problem multiplies. The bodies would be small, cold, dark, and spread through a volume of space that even powerful telescopes could not easily separate from the background. If a distant star has its own cloud of comet-like bodies, the reservoir itself would remain largely invisible. Its evidence would have to arrive through effects, through dust, through gas, through falling bodies, or through the shape of a planetary system's debris. Debris disks provide one of the more visible clues that small body reservoirs are common. Many young stars are surrounded by dusty disks, sometimes broad, sometimes ringed, sometimes shaped by planets that are themselves hard to see. The dust in these disks cannot always be primordial because small dust grains are removed over time by radiation pressure, stellar wind, and collisions. If the dust remains present, it often suggests that larger parent bodies are continually grinding down, producing new particles. A debris disk, then, can be a sign of unseen planetesimals, asteroids, comets, and icy bodies moving around another star. Beta Pictoris became one of the important names in this field. It is a young star, brighter and more massive than the Sun, located about 63 light-years away, and surrounded by a well-known debris disk. Observations of Beta Pictoris revealed not only dust, but also evidence interpreted as falling evaporating bodies, often called exocomets. These were not comets photographed with tails in the familiar way. They were inferred from changes in the star's spectrum, as gas from small bodies passed in front of the star and absorbed certain wavelengths of light. The method was indirect, but the pattern suggested comet-like objects moving close to the star. In that miniature of observation, the lesson is familiar. A small body is not seen as a world. Its presence is read from what it does to light. Around Beta Pictoris, repeated spectral signatures indicated material falling toward the star, likely released by icy or volatile-rich bodies disturbed from more distant orbits. The star's disk, planets, and exocomet evidence together made it a laboratory for thinking about how planetary systems keep and lose their small bodies. It was not the sun's Oort cloud seen from outside. It was another system showing that comet-like populations are not peculiar to the sun. The word exocomet is careful and useful. It means a comet outside the solar system, or more precisely, an object whose behavior resembles cometary activity around another star. Some are inferred from gas absorption. Others may be connected to dust production, transient dimming, or material released near a star. Their existence does not prove that every such system has an Oort cloud. It does show that icy or volatile-bearing small bodies can be scattered inward in other planetary systems, just as Oort cloud comets are scattered inward toward the sun. A returning comet is local evidence for a distant reservoir. An exocomet is distant evidence for a similar process. The comparison must remain restrained. The sun's Oort cloud is inferred from long-period comet orbits within our own system, where positions, velocities, and returns can be measured with far greater precision than around other stars. For exoplanetary systems, the evidence is thinner and more distant. A debris disk may reveal small body populations, but it does not automatically reveal the outermost reservoir. Spectral signs of falling bodies show that comet-like objects exist, but not exactly where they were stored before they moved inward. The analogy is suggestive, not complete. Still, planetary formation makes the analogy reasonable. In the standard picture, young stars form inside disks of gas and dust. Planets grow by accretion, and leftover planetesimals remain after the major planets have formed. Giant planets, if present, can scatter these smaller bodies inward, outward, or out of the system. Some bodies may be placed in belts, some in scattered disks, some in distant reservoirs. The exact outcome depends on the masses and positions of planets, the star's birth environment, and the timing of migration. But the underlying ingredients are not unique to the sun. A young planetary system is not a tidy arrangement at first. Its early disk contains more material than the mature system keeps near its planets. Large bodies disturb smaller bodies. Resonances alter paths. Close gravitational passages change orbital energy. Some material is absorbed into planets, some is broken down into dust, some is pushed into belts, and some is sent away. Around the sun, part of that outward sent material may have become the Oort cloud. Around other stars, similar scattering could produce exo-Oort clouds, though the details would vary from system to system. The birth cluster may matter as much for other systems as it may have mattered for the sun. Stars are often born in groups, surrounded by neighboring stars that later drift apart. In a crowded young environment, close stellar passages can disturb the outer regions of forming planetary systems. They can help detach scattered planetesimals into distant reservoirs, or strip some material away entirely. The same stellar encounter that helps build one reservoir might erode another, depending on timing, distance, and relative motion. An Oort cloud is therefore not only a product of planets, it is also shaped by a star's early neighborhood. This gives outer reservoirs a communal origin of sorts, though not in a sentimental sense. A star does not form in perfect isolation. Its planets and small bodies inherit the conditions of the stellar nursery, the density of nearby stars, the duration of close companionship, and the gravitational disturbances that occur before the cluster disperses. A distant comet reservoir may preserve evidence of that early setting long after the neighboring stars have moved away. In this way, the outermost small bodies of a planetary system may remember not only their star, but the company in which that star began. Some models suggest that the Sun may have captured a portion of its Oort cloud material from other stars in its birth cluster. The idea remains model dependent, but it shows how open the early outer solar system may have been. If stars formed near each other, planetesimals scattered outward from one system could sometimes become weakly bound to another. The outer reservoirs of young stars might not have been sealed private collections. They may have exchanged material through the loose gravitational conditions of their birth environment. Interstellar objects give this thought a modern edge. The discovery of One-Eye Oumuamua in 2017 and 2Y Borisov in 2019 showed that small bodies do pass between stars. Oumuamua was unusual and inactive in ways that remain debated, while Borisov behaved more clearly like a comet. Both entered the solar system from interstellar space and were not bound to the Sun. They were not Oort cloud objects in the ordinary solar sense, but they proved that planetary systems can release small bodies into the galaxy. Once released, those bodies become part of a much larger population moving between stars. The existence of interstellar objects connects Oort clouds to the galaxy more broadly. A distant reservoir can lose bodies through stellar passages, galactic tides, planetary encounters, or internal scattering. Some lost bodies may drift through interstellar space for millions or billions of years before passing near another star. Most would remain undetected. A few may enter a system at the right angle and brightness to be noticed. Their brief visits remind planetary science that the boundary between one star's small body population and the galaxy's wandering material is porous over long periods. For the Sun, the Oort cloud may be both a source and a receiver in that larger exchange. It can send comets inward, lose bodies outward, and perhaps preserve objects whose earliest history involved the Sun's birth environment. Around other stars, similar reservoirs may feed exocomets, supply interstellar objects, and slowly erode as stellar encounters reshape their outskirts. The result is a galaxy with hidden small body populations around many stars, most of them unphotographed, most of them known only through indirect signs or passing fragments. Debris disks show the younger and brighter side of this process. Around stars such as Beta Pictoris, Fomalhaut, and others, dust and structure reveal that planetesimal populations persist after the gas-rich protoplanetary disk has gone. These disks can be shaped by planets, by collisions, and by resonant structures. They are often much easier to observe than distant Oort clouds because dust closer to the star absorbs and emits radiation in measurable ways. A debris disk is not the same as an Oort cloud, but it shows that planetary systems commonly retain belts and reservoirs of small bodies after planet formation. The Sun once had such a disk of leftover material, and much of it has been cleared, incorporated, scattered, or stored. The asteroid belt, the Kuiper belt, the scattered disk, and the Oort cloud are not isolated curiosities. They are surviving expressions of the same broad process that likely occurs around other stars. A system forms, fails to use all its material in planets, and then spends billions of years redistributing what remains. The leftovers are not minor in scientific value. They are often the best witnesses to how the system reached its present shape. Exocomets have also been detected around stars other than Beta Pictoris, sometimes through transient absorption features, sometimes through unusual dimming patterns or gas signatures. Each case has its own uncertainties, and not every dip or spectral change belongs to a comet. But the growing body of evidence suggests that comet-like objects are not rare in planetary systems. Their presence supports a broader view in which icy bodies, scattered or stored at different distances, are a normal consequence of planet formation. The Sun's Oort cloud becomes local, not exceptional. This does not mean all stars possess Oort clouds like the Sun's. A star with no giant planets may scatter small bodies differently. A close binary star may disrupt distant reservoirs. A dense stellar birth environment may strip away outer material before it can settle. A low-mass star may have a different gravitational reach. A planetary system with migrating giants may create a large reservoir, while another may eject most of its icy planetesimals into interstellar space. There is no single template. The Sun's Oort cloud is one solution among many possible outcomes. The question of habitability occasionally touches this subject, but it should remain in the background here. Comets can deliver volatiles, alter surfaces, and contribute to the early histories of planets, but the relation between comet reservoirs and life is complex and not reducible to a simple gift from the outer dark. For this episode, the more important point is structural. A planetary system is larger than its planets, and its small bodies can preserve the record of formation, scattering, and long-term disturbance. Around other stars, as around the Sun, the outer architecture may be faint but consequential. The scale of these possible reservoirs changes how planetary systems are imagined. A star with planets is not merely a bright center and a few orbiting worlds. It may also have belts, dust, scattered objects, distant comets, and lost fragments moving between systems. Much of that architecture may be invisible from far away, just as the Sun's Oort cloud would be invisible to a distant observer looking back at our own system. The most extended parts of a planetary system may be the least luminous, and therefore the easiest to omit from the picture. There is a useful reversal in that thought. From Earth, the Oort cloud is remote and unphotographed. From another star, it would be almost completely hidden, perhaps detectable only through the occasional behavior of comets or the faintest statistical effects. The solar system, seen from outside, would be reduced to what instruments could measure: the sun's light, the motions of planets if they were detectable, the dust of small bodies, and perhaps the signs of comets falling inward. Our own largest reservoir would vanish into inference. This is the same condition under which other systems are studied. Other suns, then, return the Oort cloud to scale. They show that the sun's outer reservoir may be part of a galactic pattern, but also that each system's version of such a reservoir would carry its own history. Some clouds may be rich, some thin, some stripped, some never fully formed. Some may feed comets inward for billions of years. Others may have lost most of their distant bodies into interstellar space. Around every star, the balance between formation, scattering, retention, and loss writes a different outer boundary. The Oort cloud around the sun remains the only one that can be studied through local long-period comets. It is still inferred, still uncertain in detail, still beyond direct imaging, but it is close enough that its returning bodies can be measured with care. Around other stars, the same kind of reservoir is mostly a possibility read through analogy and indirect evidence. Yet that possibility enlarges the meaning of the sun's cloud. It becomes not an isolated curiosity, but one example of how planetary systems may keep their earliest material far beyond the visible arrangement of planets. By looking outward to other stars, the chronicle also begins to turn back toward the sun. The same processes that may build distant reservoirs elsewhere have shaped the one surrounding this system. Scattering, storage, perturbation, loss, and occasional return belong to a long history that began with planet formation and continues through the present. Chapter 12: The Solar System's Long Memory. The Oort cloud keeps the solar system's oldest material at its greatest distance. It is not old because it lies far away, as though remoteness itself preserved time, but because many of its bodies may have been placed there after forming among the icy planetesimals of the young planetary disk. The planets changed. Surfaces warmed, atmospheres formed, moons were shaped, impacts marked old crusts, and sunlight continued its steady work near the center. Far outward, in orbits so large that a single circuit can exceed the span of recorded civilization many times over, small bodies remained in colder storage, carrying matter from the era when the sun was still surrounded by the remains of its birth. This memory is not kept in words or in layers of writing. It is kept in chemistry, in orbit, in distance, and in survival. An icy body in the Oort cloud may carry frozen compounds that were common in the outer regions of the early solar system. Its present path may record scattering by the giant planets, later alteration by the galactic tide, and perhaps the distant effect of stars that passed the sun long before any human record began. Most of that history is not visible from Earth. It has to be reconstructed from returning comets and from the models that explain how such bodies could have been stored so far away without being entirely lost. The word memory should remain physical. The Oort cloud does not remember as a mind remembers. It preserves conditions. A body that formed near the young giant planets and was later sent outward may keep in its material composition something of the disk from which planets were made. A comet that returns after a long absence may show volatile gases, dust, and organic compounds that help scientists compare one region of formation with another. Its orbit may reveal how a distant perturbation moved it inward. The memory is therefore distributed, incomplete, and altered each time a body comes close enough to be seen. Jean Oort's 1950 proposal returned throughout this chronicle because it did something lasting. It made a remote structure scientifically necessary from the behavior of objects that were already known. Oort did not need to see a cloud in order to ask what kind of reservoir could keep supplying long-period comets. He followed the orbits backward, considered the problem of comet survival, and gave form to a region that lay beyond direct observation. The details have changed since then, and they will continue to change, but the central inference remains one of the quiet achievements of 20th century astronomy. The idea also shows how science can hold a structure without holding every detail of it. The Oort cloud is not mapped the way Mars is mapped. Its far side is not photographed. Its total mass is uncertain. Its population is estimated, and its exact boundaries remain dependent on models. Yet its existence as a distant comet reservoir is woven into the best explanations of long-period comet behavior. This is a different kind of knowledge from a surface image, less immediate but not less disciplined. It is knowledge by consequence. Over billions of years, the cloud has not simply remained unchanged. A reservoir so weakly held cannot be perfectly permanent. Passing stars have altered some orbits. The Milky Way's gravitational tide has slowly lifted and lowered others. Some bodies have been sent inward and become comets. Some have been removed from the sun's control and have entered interstellar space. Others may have shifted from one distant orbit to another, remaining bound but belonging to a different part of the cloud's broad architecture. The Oort cloud persists, but persistence does not mean stillness. The rate of change is slow enough to mislead ordinary instinct. In the inner solar system, motion is comparatively quick. Earth returns to the same part of its orbit each year. Mars takes less than 2 Earth years. Jupiter takes about 12. Neptune takes about 165. Those numbers already feel large against a human life. In the Oort cloud, orbital periods can be measured in hundreds of thousands or millions of years. A body may spend nearly all of that time near the farthest reach of its orbit, moving so slowly that, across a human generation, its place would seem almost fixed. Yet almost fixed is not fixed. The slow body continues to move. The sun continues to hold it. The galaxy continues to apply its broad tide. Neighboring stars continue their long passages through the solar neighborhood. Nothing needs to happen suddenly for the population to change. The arithmetic of time is enough. A small alteration, given 1,000,000 years, can become the beginning of an inward path. A minor increase in orbital energy, given the right geometry, can loosen an object from the sun forever. The Oort cloud is therefore both archive and source. It preserves icy bodies from the solar system's early history, and it sends a few of them inward where they can become visible. The same cloud that stores material also loses it. It feeds the inner solar system with long-period comets, then lets those comets be altered, broken, redirected, or removed. Some bodies approach the sun once and never return. Others may be captured into shorter orbits. Many more remain unseen in distant storage, never becoming part of human astronomy except as members of an inferred population. This dual role gives the Oort cloud its calm importance. It is not only a boundary, it is not only a storehouse, it is a working part of the solar system's long-term evolution, even though its activity is distributed across intervals too large to feel active. The planets move in clear, repeated circuits. The Oort cloud acts through rare returns, small perturbations, gradual depletion, and enormous numbers. It is a slow system, but not an inert one. A distant comet returning from the cloud briefly compresses all of this scale into visibility. For most of its orbit, it is beyond reach, cold and faint. Then it moves inward, warms, forms a coma, releases dust, and becomes an object that can be tracked, measured, and sometimes seen. Its brightness may last for weeks or months. Its orbit may point back toward a path millions of years long. The visible comet is therefore a short sentence spoken by a very old reservoir. There is no need to force that sentence into certainty. A single comet cannot reveal the whole cloud. Its surface has been changed by heat, its orbit may have been revised by planets, and its history may include influences that cannot be reconstructed in full. But many comets gathered across time can reveal patterns. Their inclinations, energies, periods, and chemistry become a partial record of the distant population. The Oort cloud is read not through one return, but through the continuing accumulation of returns. The future will add more pieces to this reading. Wider surveys will discover more faint comets, more distant trans-Neptunian objects, and perhaps more bodies that occupy the uncertain region between the scattered disk and the inner Oort cloud. Better computing will refine models of stellar passages, galactic tides, and early planetary migration. New instruments may detect objects now below the threshold of visibility. The cloud may become more constrained, more layered, and more complex than the original picture suggested. It will still remain difficult to see as a whole. This difficulty is part of its meaning. Some places in the solar system are known by encounter. A spacecraft passes, a surface is imaged, a crater is measured, a moon is mapped. Others are known by return. The Oort cloud belongs mostly to the second kind. Its bodies come back one at a time, carrying pieces of a region no probe has entered and no telescope has framed. The reservoir remains distant, but it is not disconnected. Its evidence passes through the inner solar system, becomes warmed by the same sun that holds Earth in orbit, and then fades again into altered paths. The scale also changes the emotional temperature of the solar system. Close to the sun, the system feels full of worlds. Mercury's scorched surface, Venus under cloud, Earth with oceans and air, Mars with dust and ice, the giant planets with rings, storms, and moons. Beyond them lie belts, scattered bodies, dwarf planets, and then the faint extension of the sun's reach. The Oort cloud does not add a bright world to this list. It adds depth. It says that the solar system is not finished when the planets are named. At the farthest margins, belonging becomes delicate. A body may remain with the sun for billions of years, then leave after a stellar passage. Another may drift inward after a small adjustment, and become visible for the first time since the formation of civilization. A third may stay remote for the remaining life of the sun, never warmed enough to produce a coma, never detected, never counted except in estimates. The cloud's population contains all of these possibilities. It is a place of retention and release. The sun itself will not remain unchanged forever. Over very long future spans, it will brighten, age, and eventually leave its present main sequence state. Those changes belong to a future much larger than the human horizon, and the Oort Cloud's distant bodies will respond to the sun's evolving mass and gravity in ways that may loosen many from their old orbits. The solar system's long memory is not eternal. It is long enough to exceed ordinary thought, but still part of a changing star system. For now, the cloud remains mostly cold and unvisited. The planets continue their shorter circuits near the center. The Kuiper belt keeps its nearer archive of icy bodies beyond Neptune. Voyager spacecraft move outward through interstellar plasma, still far from the cloud's inner distances. Long-period comets arrive now and then, brightening briefly, losing material, and carrying orbital evidence from the outer reservoir into the region of telescopes and instruments. The old structure continues to be inferred, revised, and approached through the bodies it sends back. The scale that seemed impossible at the beginning has become the final shape of the subject. One astronomical unit began as a useful measure, the Earth-Sun distance repeated outward to Neptune, Pluto, the Kuiper belt, and beyond. Then that measure itself became small against the Oort Cloud's possible reach, thousands and tens of thousands of astronomical units from the sun. The planets became the inner arrangement. The heliopause became one boundary among several. The Oort Cloud became the broad gravitational margin where the solar system thins into the galaxy around it. Seen this way, the Oort Cloud is not a final wall. It is a fading population, a distant memory of formation, a reservoir slowly shaped by the sun, the planets, passing stars, and the Milky Way. Most of its bodies remain where they are, moving through long arcs under weak sunlight. A few are disturbed into return. A few are lost. Across the largest spans, the cloud changes by almost imperceptible degrees, and those degrees are enough. Far from the planetary region, an icy body continues along its slow orbit. The sun is still the center of its motion, though not the bright authority known near Earth. Around it, other unseen bodies follow their own wide paths, separated by distances too large for nearness to have ordinary meaning. The galaxy supplies its faint tide. Passing stars alter the outer margins over ages. Nothing in the scene needs to announce itself. The motion continues. The reservoir remains mostly unlit, mostly unmeasured, and still part of the solar system. Its bodies keep the cold record of early scattering, and the occasional comet carries that record inward for a short season before returning, changing, or leaving. In the outer dark, there is no clear line where the sun's family ends, only a gradual thinning of influence, a wide dispersal of ancient ice, and the long, steady patience of orbits that continue while the inner worlds move through their smaller years. The journey is complete. Rest well. Read only when a small body comes back toward light